Studies measuring identical meals at different times of day consistently show glucose spikes 20 to 40% higher in the evening than in the morning. Same food, same digestive system, same person. The difference is not the food. The difference is not portion size, not preparation method, not whether you ate it with butter or without. The difference is a circadian oscillation in insulin sensitivity that peaks in the morning and declines across the day, governed by the suprachiasmatic nucleus in the hypothalamus, amplified by melatonin onset in the evening, and executed by clock genes operating inside the insulin-producing cells of your pancreas. Your body processes food differently depending on the position of the sun. After dark, the same meal becomes a different metabolic event. Every dietary conversation you have ever had with a doctor, a nutritionist, a magazine, a well-meaning family member has focused on what you eat, calories, macronutrients, glycemic index, sugar content, fat content, fiber, sodium, cholesterol. The conversation has been about the composition of the food on the plate. And the conversation has been incomplete. Not wrong, but incomplete in a way that may account for a significant portion of the metabolic variation the dietary advice was trying to address. Because the metabolic response to that food, how much insulin your pancreas secretes, how efficiently your muscles absorb glucose, how your liver processes fructose, how your gut microbiome ferments the fiber, how many calories your body burns digesting the meal, changes across the day by magnitudes that dwarf the difference between most dietary choices. The when is not a footnote to the what. For glucose control specifically, the variable that determines pre-diabetic and diabetic status, the when may be the larger variable. A moderate meal at noon may produce a better glucose response than a low-carbohydrate meal at 9 in the evening, because the circadian advantage of morning eating is large enough to offset the dietary advantage of carbohydrate reduction. Your pancreas does not produce insulin at a constant rate. The beta cells in the islets of Langerhans, the clusters of endocrine cells scattered through the pancreatic tissue, follow a circadian rhythm that is independent of when you eat. Insulin secretion capacity peaks in the morning and declines progressively through the afternoon and evening. This rhythm is not learned. It is not driven by habit or by eating patterns. It is driven by clock genes, BMAL1, CLO, CPEAR, CRY, the molecular oscillators that govern every circadian process in the body, operating inside the beta cells themselves. Marcheva and colleagues published in Nature in 2010 that disruption of the pancreatic clock gene, BMAL1, in mice produced complete loss of circadian insulin secretion, glucose intolerance, and eventual diabetes from clock disruption alone. No change in diet. No change in caloric intake. No change in physical activity. The clock gene was disrupted and the metabolic system collapsed. The pancreas lost its ability to match insulin output to the time of day. It could no longer distinguish morning from evening, could no longer ramp up production when the feeding window opened, could no longer scale back when the fasting window began. The glucose accumulated. The diabetes developed. The cause was not food. The cause was time. That finding, diabetes produced by clock disruption alone without any change in diet or activity, is the finding that moved chrononutrition from a footnote to the center of the metabolic conversation for me. Think about that finding in the context of human type 2 diabetes. The standard clinical narrative focuses on insulin resistance, the tissues becoming less responsive to insulin, requiring the pancreas to produce more, eventually exhausting the beta cells. The Marcheva data adds a dimension the standard narrative omits. The circadian oscillation in insulin production means the pancreas is designed to work hard in the morning and rest in the evening. A person who eats their largest meal in the evening is demanding peak insulin output during the window when the beta cells are programmed for their lowest production. The beta cells are not merely responding to a glucose load, they are responding to a glucose load that arrived during their rest period. The demand-supply mismatch is circadian, not just metabolic. Your pancreas is most responsive to glucose in the morning. Insulin secretion is fastest. The beta cells detect the glucose rise and release insulin with minimal delay. Insulin sensitivity in target tissues is highest. The muscle cells, the liver cells, the fat cells or respond to the insulin signal with maximum efficiency. Glucose clearance is most rapid. The glucose enters the blood, the insulin arrives, the tissues absorb it, and the blood glucose returns to baseline within the expected window. By evening, every component of this system has slowed. The beta cells respond more sluggishly. The tissues respond less completely. The glucose stays in your blood longer, the spike is higher. The return to baseline takes longer. The difference is not marginal. Sutton and colleagues published in Cell Metabolism in 2018 a controlled feeding study that isolated the timing variable with unusual precision. Participants ate identical meals, identical in every respect, at different times of day. Morning eating improved insulin sensitivity, reduced 24-hour glucose levels, and lowered blood pressure compared to evening eating. No difference in calories, no difference in macronutrient composition, no difference in physical activity, no difference in sleep duration. The only variable was when the food arrived, and the metabolic outcomes diverged by magnitudes that would justify a dietary intervention if they had been produced by a change in food composition rather than a change in timing. Sutton data is the cleanest demonstration of the chrononutrition principle in humans because it controls for everything except time. Most dietary studies confound timing with composition, with caloric intake, with activity levels, with compliance variation. Sutton held everything constant except the clock. The clock was sufficient to produce the divergence. The implication, a person who eats well but eats late, may produce worse metabolic outcomes than a person who eats moderately but eats early. The timing can override the quality, not because timing matters more than quality in all cases, but because timing operates on a different axis entirely, and ignoring it leaves a major metabolic variable uncontrolled. Think about what that means for every blood glucose measurement you have ever received. If your doctor noted elevated fasting glucose or impaired glucose tolerance, the standard response is dietary modification. Eat less sugar, reduce carbohydrates, increase fiber, choose whole grains over refined ones. These are valid interventions. They address the composition of the food. But they address the what without addressing the when, and the when may account for a larger portion of the glucose variation than the what. A person who eats a moderate carbohydrate meal at noon may produce a normal glucose response. The insulin arrives quickly, the GLUT4 transporters are available, the glucose clears within the expected window. That person eating an identical meal at 9 in the evening may produce a response that crosses the pre-diabetic threshold, not because their pancreas is broken, but because their circadian clock has shifted the pancreas into its rest mode and the muscle has retracted its glucose transporters. The blood sugar problem may be partly a timing problem. The dietary advice may be incomplete without the chronobiological context. Person over 65 who has been managing type 2 diabetes or prediabetes through dietary restriction, who has eliminated foods they enjoy, who has counted carbohydrates at every meal, who has felt the daily friction of a restricted diet, may find that meal timing provides a metabolic lever that dietary composition alone does not. Moving the largest meal from evening to morning, without changing a single food item on the plate, produces a measurable improvement in glucose control that no equivalent dietary substitution achieves at comparable magnitude. The timing is not a replacement for dietary quality. It is an additional variable that most dietary advice ignores entirely. Now, melatonin. Because the evening decline in insulin sensitivity is not merely a gradual fade, it accelerates sharply when melatonin enters the picture. Melatonin, the hormone that initiates sleep preparation, begins rising approximately 2 hours before your habitual bedtime. For most adults over 65, melatonin onset occurs between 7 and 9 in the evening, earlier than most people assume and earlier than most people finish eating. Melatonin receptors, designated MT1 and MT2, are expressed on pancreatic beta cells. When melatonin binds these receptors, it directly inhibits insulin secretion. The beta cell receives the signal and reduces its output. The glucose that arrives after melatonin onset meets a pancreas that has been told by its own receptors to slow down. This is not a side effect. It is not an accidental interaction between two unrelated hormonal systems that happen to overlap in the evening. It is a coordinated metabolic shutdown, the body preparing for the fasting state of sleep by deliberately reducing its capacity to process incoming nutrients. The digestive system is scheduled for rest. The pancreas is complying with the schedule. The melatonin is the signal that initiates the compliance. Eating after melatonin onset is delivering glucose to a system that has already received the instruction to stop processing it. The factory has sent its workers home, and the delivery truck has arrived at the loading dock. If you have ever noticed that a late dinner sits differently than an early one, heavier in the stomach, less satisfying, followed by a restless night rather than a settled one, you have noticed the melatonin-insulin interaction without knowing its mechanism. Your subjective experience was accurate. The food was meeting a different metabolic environment. The pancreas was operating at reduced capacity. The glucose was clearing more slowly. The body was telling you, through the discomfort, that the timing was wrong. Garrelay and colleagues published in the Proceedings of the National Academy of Sciences in 2015 that a common genetic variant in the melatonin receptor gene, MTNR1B, increased the risk of type 2 diabetes, specifically through impaired evening glucose tolerance. Carriers of this variant had stronger melatonin-mediated beta cell suppression. Their pancreas shut down more aggressively in the evening, producing larger glucose spikes from identical food. The interaction between melatonin and insulin is not marginal. It is a primary metabolic pathway that makes late eating fundamentally different from early eating at the hormonal level. The genetic finding confirms what the physiology predicts. The evening pancreas is a different organ from the morning pancreas. Melatonin makes it so, you see, and the pancreas is only one system. Because the circadian variation in metabolic capacity runs through every organ involved in processing food. The muscle, the liver, the gut microbiome, the nervous system, all keep one schedule. All favor the morning. Skeletal muscle is responsible for approximately 80% of insulin-mediated glucose uptake. The muscle is where most of the glucose goes after a meal, and therefore where most of the circadian variation in glucose clearance originates. The GLUT4 transporters that move glucose from blood into muscle cells are more abundant at the cell surface in the morning than in the evening. A circadian variation in GLUT4 translocation that has been documented in both animal and human studies. Morning muscle is metabolically primed. The glucose transporters are positioned at the cell membrane, ready to bind insulin and shuttle glucose into the cell. Evening muscle has fewer transporters at the surface. The glucose arrives, but the machinery to absorb it has partially retracted into the cell interior. The muscle is less willing to take up the glucose. More of it stays in the blood. The spike is higher and longer, not because the pancreas failed to produce enough insulin, but because the muscle failed to respond to the insulin with morning efficiency. This is the distinction between insulin production and insulin sensitivity, and the circadian clock affects both. The pancreas produces less insulin in the evening. Production decline. The muscle responds less to the insulin. The pancreas does produce, sensitivity decline. Two independent mechanisms, both declining across one daily arc, compounding each other's effect on blood glucose. The morning system works on both ends. More insulin produced, more glucose absorbed. The evening system fails on both ends. Less insulin produced, less glucose absorbed. The 20 to 40% glucose difference is the combined result of both mechanisms operating simultaneously. Cortisol contributes to the morning advantage through a mechanism, the entropy discussion identified in a different context. Cortisol peaks within 30 to 60 minutes of waking. The cortisol awakening response? This peak is not a stress event. It is a metabolic mobilization. Cortisol increases hepatic glucose output, enhances fatty acid mobilization from adipose tissue, and upregulates metabolic enzyme activity in the liver, the gut, and the peripheral tissues in preparation for the day's energy demands. Eating during this cortisol window delivers nutrients to a system that is metabolically primed and fully staffed. Enzymes are active. Blood flow to the gut is high. The liver is operating at peak capacity for nutrient processing, glycogen synthesis, gluconeogenesis regulation, amino acid metabolism, lipid processing, all running at their circadian maximum. By evening, cortisol has declined to its circadian trough. The metabolic mobilization is over. Hepatic enzyme activity is reduced. The liver has down-regulated the processing machinery it was running at full capacity 12 hours earlier. The liver's capacity to process incoming nutrients, particularly fructose and alcohol, which require hepatic first-pass metabolism through enzyme pathways that are circadian regulated, is diminished. Fructose, arriving at the liver in the evening, meets reduced fructokinase activity and is more likely to be converted to triglycerides and stored as intrahepatic fat than fructose arriving in the morning, which meets peak enzyme activity and is more efficiently processed through oxidative pathways. And here is the connection to a pattern that has puzzled hepatologists for 2 decades. Non-alcoholic fatty liver disease has established risk factors: excess calories, insulin resistance, obesity, genetic lipid metabolism variants. The timing dimension does not replace these, but the circadian variation in hepatic processing capacity adds a variable the standard NAFLD conversation does not address. Identical caloric loads may produce different hepatic fat accumulation depending on when the liver receives them. The person who eats a large dinner at 9 in the evening and a small breakfast at 7 in the morning has inverted the circadian eating pattern, loading the liver during its lowest performance window and leaving it idle during its highest. The liver stores what it cannot process at the reduced enzyme capacity of the evening. The storage accumulates. The fatty liver develops, not solely from excess calories in the 24-hour total, but potentially from calories arriving during the window when hepatic processing capacity is at its minimum. Well, and the gut microbiome keeps this schedule. Your intestinal bacteria do not maintain constant populations across the day. Different species dominate at different hours. A circadian oscillation in microbial composition documented in both mice and humans that affects how identical food is fermented, absorbed, and metabolized depending on when it arrives in the intestine. Tice and colleagues published in Cell in 2014 that the gut microbiome in mice exhibits robust circadian rhythms. Certain bacterial species peak in abundance during daytime feeding periods and decline during nighttime fasting periods. The oscillation is not random variation. It is synchronized to the host's circadian clock through feeding timing, bile acid secretion patterns, and autonomic nervous system signaling to the gut wall. When Tice disrupted the host clock through simulated jet lag and irregular feeding schedules, the microbial oscillation flattened. The normal day-night variation in bacterial populations collapsed into a uniform, dysbiotic community that was associated with metabolic dysfunction, increased caloric extraction from food, and weight gain. Weight gain deserves attention because of what it reveals about the relationship between timing and energy extraction. The mice with disrupted circadian clocks ate identical food in identical quantities as the controls. They gained more weight. The explanation: the dysbiotic microbial community that formed when the circadian oscillation was disrupted extracted more energy from identical food. The bacteria that dominate during the disrupted state are more efficient at breaking down complex carbohydrates and extracting calories that the normal daytime bacterial community would have left undigested. Circadian disruption changed, not just how the host processed the food, but how the microbiome processed it, a double shift in metabolic efficiency from a single timing variable. Tice's finding is in mice. The circadian microbiome oscillation has been confirmed in humans, but the weight gained from circadian disruption at controlled caloric intake has not been replicated in human studies with equivalent precision. The direction is consistent across species. The magnitude in humans remains to be measured. Food you eat at noon is fermented by a different microbial community than the food you eat at midnight. The short-chain fatty acids produced, the bile acid modifications performed, the vitamin synthesis conducted, all vary based on which bacterial species are dominant at the time of arrival. Your gut bacteria keep the schedule your pancreas does. They are most metabolically active during the day. Feeding them at night delivers substrate to a shift that is already clocked out, and the skeleton crew that remains extracts more calories from it than the day shift would have. And then the thermic effect. Because your body does not burn an equal number of calories processing an identical meal at different times of day, the energy cost of digestion itself, the calories your body expends to break down, absorb, transport, and metabolize the nutrients in a meal, varies with the circadian clock in a way that no calorie counting system accounts for. Richter and colleagues published in the Journal of Clinical Endocrinology and Metabolism in 2020 that diet-induced thermogenesis, the energy your body expends to digest, absorb, and metabolize a meal, was 2.5 times higher in the morning than in the evening for identical meals. The magnitude varies across studies. Richter's finding represents the high end of measured variation, with other studies reporting morning thermogenesis 30 to 100% higher than evening. The direction is consistent across every study that has measured it. The body burns more energy processing morning food than evening food. The magnitude is large enough to matter metabolically, regardless of which study's figure you use. Mechanism involves sympathetic nervous system activity, which is higher in the morning as part of the cortisol-mediated metabolic mobilization and lower in the evening as part of the parasympathetic transition to rest. Higher sympathetic tone drives greater thermogenesis. The body runs hotter metabolically when the sympathetic system is engaged. Lower sympathetic tone reduces thermogenesis. The body conserves energy during the evening parasympathetic state, processing the incoming nutrients at minimum metabolic cost. Consider what this means arithmetically. A meal that costs your body 100 calories to process in the morning may cost 50 to 70 calories to process in the evening. Identical food, identical portion, identical macronutrient profile. The difference sounds small on any single meal. Over a year of shifted eating, breakfast skipped or minimal, lunch light, dinner, the largest meal of the day, the cumulative difference in thermic effect alone represents thousands of calories that were processed at reduced metabolic cost because they arrived during the low thermogenesis evening window. The calorie on the nutrition label is a laboratory measurement, the energy released when the food is burned in a calorimeter. The calorie your body extracts is a circadian variable. The label does not change with the clock. Your metabolism does. Research converges from multiple directions on one conclusion. Panda and colleagues at the Salk Institute published in Cell Metabolism in 2012 that restricting food intake to a 10 to 12 hour daytime window without changing caloric intake, without changing food composition, without any dietary restriction beyond timing, produced significant metabolic improvements, reduced body fat, lower glucose, improved lipid profiles, reduced inflammation. The mechanism was not caloric restriction. It was circadian alignment. The eating window was synchronized with the period of highest metabolic capacity, and the fasting window was synchronized with the period of lowest metabolic capacity. The body received identical fuel. The timing allowed it to process the fuel with the machinery that was actually running. Panda finding is worth dwelling on because it isolates the timing variable from every other dietary variable. Calories were held constant. The subjects ate an identical total amount. Macronutrients were held constant. The food composition did not change. Physical activity was held constant. The only variable that changed was when the calories arrived, and the metabolic outcomes improved across every marker measured. Body fat decreased, fasting glucose decreased, triglycerides decreased, inflammatory markers decreased from timing alone. Fasting discussion covered autophagy, the cellular recycling program that activates during the fasting window when mTOR is inhibited and AMPK is active. The chrononutrition data adds a layer that the fasting discussion did not address. The fasting window is not just a period when autophagy operates. It is also the period when the metabolic machinery has shifted into its low capacity mode, and food arriving during this window is processed at reduced efficiency with increased metabolic cost to the body. The fasting window and the low metabolism window overlap by evolutionary design. The body fasts at night because the metabolism is designed to rest at night. Breaking the fast during the rest window imposes a double cost. The autophagy window is shortened, and the food that shortened it is processed by machinery running at reduced capacity. The circadian alignment of eating is not merely a metabolic optimization. It is the alignment of fuel delivery with the operating schedule of every organ that processes fuel. That convergence, pancreatic insulin rhythm, melatonin-mediated beta cell suppression, GLUT4 transporter cycling in the muscle, cortisol-driven hepatic mobilization, microbiome circadian oscillation, and thermic effect variation, all declining across one daily arc, all favoring morning metabolism over evening metabolism through independent mechanisms governed by one master clock, is the pattern the metabolic literature had been missing. Because it means the dietary advice that focuses exclusively on what you eat is addressing half the equation. The other half is when you eat it. And the when is governed by physics. The plate of food cannot override clot genes in the beta cells, melatonin receptors on the pancreas, GLUT4 cycling in the muscle, bacterial oscillation in the gut, sympathetic tone in the nervous system. 6 systems, 6 independent circadian oscillations, all peaking in the morning, all declining by evening, all governed by the suprachiasmatic nucleus responding to light through melanopsin receptors in the retina. The food does not change, the body that receives it does, every hour, on a schedule that sunlight calibrates each morning and melatonin enforces each evening. The schedule is not a suggestion the body can ignore. It is the operating program of every metabolic organ, written in clock genes that have been oscillating in every cell since the first organism distinguished day from night. Practical application requires no calorie counting, no food elimination, no subscription, no app, no willpower beyond rearranging the timing of meals you are already eating. It requires a clock and the understanding that your pancreas, your liver, your gut microbiome, your muscle tissue, and your sympathetic nervous system are all keeping one schedule, and that schedule favors the morning. Research consistently points in one direction. Glucose control improves when the largest caloric load arrives during the window of highest metabolic capacity. Populations studied by Sutton and Panda showed measurable improvement when the eating window was compressed into the first 10 to 12 hours after waking, with the heaviest meal early. The practical implication is rearrangement rather than restriction. The meal you have been eating as dinner would produce a measurably better metabolic outcome at noon. No change in food. No change in quantity. The identical meal, moved 12 hours earlier in the day, evening eating that finishes before melatonin onset, before 7 for most adults, allows the pancreas to shift into its rest mode with nothing in the pipeline that requires its attention. The lighter the evening meal, the less glucose arrives during the suppressed insulin window, the lower the spike, the less the liver is forced to store what it cannot process. The transition from fed to fasting is clean when it aligns with the transition from metabolic activity to metabolic rest. Window between melatonin onset and sleep is the period of lowest metabolic capacity your body produces in any 24-hour cycle. Food arriving in that window meets a pancreas that has been told to stop, muscle that has retracted its glucose transporters, a liver operating at reduced enzymatic capacity, a microbiome that has changed shifts, and a nervous system that burns fewer calories processing the meal. The food is identical to what you ate at noon. The metabolic event is not. Same bread, same body, same body. 20 to 40% difference in glucose response. The only variable was the clock. Your pancreas knows what time it is. Clock genes in the beta cells oscillate with a period of 24 hours, peaking insulin production in the morning and reducing it by evening. Your melatonin shuts down insulin secretion every evening on the schedule it has kept for your entire life, binding to receptors on the beta cells that no dietary intervention can override. Your GLUT4 transporters retract from the muscle cell surface as the day progresses. The glucose that arrived at noon met transporters ready to receive it. The glucose that arrives at 9 meets a reduced complement. Your gut bacteria chain shifts. The daytime community that ferments and processes efficiently yields to an evening community that extracts more calories from less food. Your liver clocks out. The enzyme activity that processed fructose and lipids at peak efficiency 12 hours ago has declined to its circadian minimum. Your sympathetic nervous system has shifted to parasympathetic dominance. The thermogenic cost of digesting the meal has dropped to a fraction of its morning value. The meal you eat at 8 in the evening is not the meal you think you are eating. It is the same food meeting, a different body, a body that has already begun shutting down every system required to process it. The clock is not optional. The clock is not negotiable. The clock is the metabolism.